Okay, so good morning, everyone. We had started to discuss the state space modeling for various physical systems, mechanical systems, and electrical systems. So the state space model is another way of mathematically representing the physical systems. So we modeled our standard mechanical system with force applying on the mass with friction and spring. And we got the state space model by defining x1 of t as position and x1 of t as velocity and x2 of t as position. So we arrange the differential equation f of t minus b x dot of t minus k x of t equal to m x double dot of t in the form of x dot equal to ax plus du and y is equal to cx plus du. So we just put it in that format. So that is called as the state space model. We also modeled our series RLC circuit. So first we modeled it using x1 of t as dvc by dt, x2 of t as vc of t. So we rewrote the entire KVL equation in terms of V in and V naught. Or V naught is nothing but Vc. So dVc by dt as the first variable and Vc of t as the second variable. We could write the state space model because derivative x1 dot of t will be d square Vc by dt square. So express d square Vc by dt square by dividing by LC and taking d square Vc by dt on the left hand side, we get minus R by L minus 1 by LC as the first row and plus 1 over LC into Vn of t. And x2 dot is simply x1 of t. So x2 dot equal to x1 of t, therefore second row becomes 1, 0. The alternate way is defining x1 of t as the loop current and x2 of t as Vc of t, then x1 dot of t is equal to di by dt loop current. So just get an expression for di by dt in terms of the other variables. Then it will be minus R by L and minus 1 by L as the first row, and x2 dot is dVc by dt is 1 by C into loop current. So 1 by C into x1 of t. So that means for a given physical system, we were able to write two state space models. So there are other ways of writing the state space models also, like you could have defined x1 of t as Vc of t and x2 of t as IL of t. Then again, the arrangement in the A matrix would be different. A and B matrix will be different. Okay, so that means the state space model is not unique. It depends on how you define your state variables. Okay. However, we have seen that for the given input-output pair, the transfer function for the given system is unique. Okay. So transfer function model is unique. State space models can be many. So therefore, we need to understand what is the relation between the state space model and the transfer function model. Okay. So remember that the transfer function model is an input-output relation. And state space model is a time domain model, and transfer function model is a S domain model. Transfer function model is a ratio of y of s to u of s. That means this x, which is the state vector, has no role to play in the transfer function model. Okay, so therefore, if you want to obtain the transfer function model from the state space model, okay, we need to eliminate this state vector x and only relate input and output. Okay, so we will obtain the relation from the state space model to the transfer function model. That is, we will express the transfer function in terms of the state space model parameters. Okay. So to do that, so state space model is in the time domain model. Therefore, you need to apply Laplace transform to go to the S domain model. So S into x of s minus x of 0 is equal to a x of s plus b u of s. Okay. So in the transfer function model, it's a ratio y of s to u of s. Therefore, x of s need to be eliminated. Eliminated in the sense we need to express x of s in terms of u of s. Then we can then substitute wherever there is x, we can just write it in terms of u and get a whole equation only in terms of y and u. So we have s x of s minus x of 0 equal to a x of s. So you take x of s terms on one side. So it will be s into x of s minus a x of s equal to b u of s. Okay, in the transfer function, we consider the initial conditions to be 0. Okay, therefore you can take x of 0 as 0. And s into x of s, we can write it as s into identity matrix into x of s. Okay, so identity matrix plays the role of unity. Number one, unity is in as in the scalar. Okay, in the matrix case, it becomes an identity matrix of n cross n. So s into x of s is same as s into I into x of s, where I is the identity matrix of size n cross n. So remember that all these are vectors and matrices. So s into I into x of s minus a x of s equal to b u of s. Therefore, si minus a into x of s equal to x of 0 plus bu of s if x of 0 is non-zero. If it is 0, then it is simply si minus a x of s equal to bu of s. So s into I into x of s minus a x of s is equal to p u of s. Yes, actually. So I can take si outside, si minus a into x of s. Okay, so notice that si minus a is a n cross n matrix. n matrix times x of s so x of s is n cross 1. Okay, so what is x of s? Where it is coming from? X of s is Laplace transform of vector, right? Laplace transform of x1 of t Laplace transform of x2 of t so that is why it is n cross 1 vector. Okay, so it is equal to b times u of s. So again b is n cross 1 into u of s. So next we need an expression for x of s. So therefore what is x of s? From the previous equation, x of s, how do you write x of s? If you take the output equation is what? Y of t is equal to c times x of t plus d into u of t. This is the output equation. Yeah, Shruti is right. Okay, so if you take Laplace transform of this, we have y of s is equal to c x of s plus du of s, right? So if you want transfer function, we don't want this x of s, right? So we need to express it in terms of u of s. So what is x of s from this previous equation? We need to pre-multiply this equation by si minus a inverse. Okay, so this is a matrix equation. Okay, you cannot simply do a division. Simple division is not allowed. You need to pre-multiply by si minus a inverse. So pre-multiplying by si minus a inverse, we get x of s equal to si minus a inverse into b u of s. Okay. Then wherever x of s is there, you put this si minus a inverse into b u of s, and then you can divide by u of s. Here we can do the simple division because u of s is a scalar quantity. Okay, therefore no need to write u inverse, right? Pi of s by u of s equal to c si minus a inverse into b plus d. Okay, so that means if you know the ABCD parameters, you can obtain the transfer function of the system. So we go back to our example and verify the transfer function. We obtained the transfer function in the first week of this course for the mass spring system. Okay, so same transfer function we obtain by the ABCD parameters. Okay, so what are the A matrix? A matrix was minus B by M, minus K by M, 1, 0, 1 by M, 0. Okay, first, I'm going to rewrite again. So A matrix is minus B by M, minus K by M, 1, 0. So first, write S into identity matrix. S into identity matrix. So that is equal to, it's a 2 cross 2 matrix. Therefore, we have S in 0 and 0 S. Okay, so it's not 5. So this is Si, and A is minus B by M minus K by M, 1, 0. We had used for friction coefficient, I think we had used Kf. Okay, so we can use either Kf or we can use B. Minus spring coefficient also, sometimes we use Ks, a subscript S we use. A 1, 0. So what is Si minus A? Si minus A is again going to be another 2 cross 2 matrix. And that is equal to S plus B over M K by M minus 1 and S. Okay, So to find the transfer function, then we need to find the inverse of this Si minus A inverse. So what is adjoint of Si minus A? Adjoint of so you need to find the cofactors. So S plus B by M and here it is going to be minus of minus 1, so it is plus 1, and here it is minus K by M. So these are all the cofactors, and you need to take the transpose of this. Okay, so that is equal to S 1 minus K by M and S plus B by M. Any questions? Any question? So if I multiply, okay, then we have determinant of Si minus A, because if you want, yeah, just write. Will be equal to, okay, S into S plus B by M minus of minus into K by M. Okay, so it is S square plus B by M into S plus K by M. Okay, so that goes into denominator of the transfer function, because C Si minus A inverse into B is nothing but C adjoint of Si minus A into B divided by, okay, D is 0, that is why we are not worried about D in this example. So D, C adjoint of Si minus A into B. Interchange the diagonal and change sign of Yeah, that's right. You can do that only for a 2 cross 2 matrix. So you need to be careful when you go for a 3 cross 3 matrix. That's why I'm giving you the procedure to find the adjoint. You need to find the cofactors and then take the transpose. So that means in case of 2 cross 2, it will be just changing the sign of the non-diagonal elements. Okay. Any other question? So numerator part is C adjoint of Si minus A into B. Okay. So plus D is there. That we will not worry about because D is 0 in this model. So this will be equal to maybe later. It is available in any standard matrix book, second PUC book. How to find the cofactors, how to find the adjoint. It's available in any 12th standard book. Okay, so C is 0, 1. Okay. So I can do first with the 0, 1 into the adjoint, it is S minus we will do. I think in the event 4 there are that I have given there are. Yeah. Okay, I will do one example in the class. In the event 4, I have given some examples with the third order state space model. Okay, so 1 S plus B by M. So that means when you multiply 0, 1 with any matrix, you are basically going to get the second row of the matrix. Okay, so if it's a third order system, if it is 0, 0, 1, then that means when you pre-multiply by 0, 0, 1, you will get a third row of the matrix. Okay, then we also have this B. B is 1 by M. B is 1 by M, 0. And 0. Okay, so when you multiply by 0, 1, you get 1 S plus B by M. And then, so it is nothing but 1 S plus B by M. So it is 1 over m 0. So it is simply, this is equal to 1 by m. Okay. So numerator is 1 by m, denominator is s square plus b over m into s plus k by m. Okay, so that is the transfer function we got in the first week of this course. Any question? Okay, any question on this? So we'll similarly derive the transfer function for the circuit. Okay, so the transfer function is 1 over LC s square plus R over LS plus 1 over LC. So we get this again by this method. So if A is minus R by L minus 1 by LC 1 0, okay, so I will not do it, I will just explain. So it is S plus R by L 1 by LC, so S plus R by L. So if it is minus R by L minus 1 by L in the second case, and it is S plus R by L 1 by L minus 1 by C S whole inverse 1 over L 0. Okay, so if you take the adjoint again, S will come here, S plus R by L will go to 2 comma 2, and this will be minus 1 by L and 1 by C. So if you take, if you multiply by 0, 1, you will get 1 over C into S plus R by L, 1 over, so ultimately you will get 1 over LC in the numerator. Next. And the determinant is S square plus R by LS plus 1 over LC. So you will get the same thing if you use the other state space model. Minus R by L minus 1 by LC, 1 by LC, 0. Okay, so two state space models are for the same circuit, RLC circuit. And if you apply C Si minus A inverse into B plus D, you get the same transfer function. Okay. So whether you use this state space model or you use this state space model using different state variables, okay, you get the same transfer function. That is the main point in this that you need to understand. Any questions? I will discuss DC motor example. So if you check your previous notes, we described all the variables in the DC motor: armature resistance, armature inductance, armature current, back EMF. Okay, so what is the principle of operation? You have law of motor and law of generator. And now, because of law of generator, back EMF is generated when you have a rotating thing perpendicular to the magnetic field. Okay, back EMF is generated. So that is equal to K2 times d theta by dt. By KVL, V in of t equal to LdI by dt plus R into I of t plus the EMF generated. And because of law of motor, okay, if there is a current carrying conductor perpendicular to the magnetic field, torque is generated. Okay, and so torque generated is proportional to the current in the conductor. And torque equation is induced torque minus opposing torque is equal to moment of inertia into angular acceleration. So if the variable of interest is the velocity, okay, angular velocity d theta by dt, then we can express everything in terms of that omega of t equal to d theta by dt. Okay, then the equations will become b times omega of t plus j d omega by dt, and eb of t equal to k2 into omega of t. So carefully observe these equations, understand the equations. So then the thing is here, it's an electromechanical system. So both the electrical and mechanical are coupled here. And we have one differential equation of the first order here, another differential equation which is also of the first order if you consider omega of t. Okay, so we have two equations, two differential equations, and they are a first order differential equations. Okay, see, in the previous example what happened, we had a second order differential equation. Okay, here also you can consider like that. You have one first order differential equation here, another first order differential equation here. Of course, if you substitute IL of t in the previous equation, whole equation will become second order differential equation. That is why we went for the two state variables. Okay, so the same concept here. Here we have one differential equation of the first order, another differential equation of the first order. So therefore, define using two state variables. Followed? That is, if you are considering the angular velocity, then you have the first order differential equation. Here, one first order differential equation with respect to torque, another first order differential equation with respect to voltage. So two first order differential equation. Therefore, define two state variables. Okay. So we define x1 of t as omega of t and x2 of t as I of t, because we have the expression for d omega by dt here in the torque equation, and we have expression for di by dt in the voltage equation. Okay, so that is why we are choosing those two state variables. then express d omega by dt as, you know, minus b by j omega of t, to d omega by dt is equal to minus b by j omega of t plus k1 by j, k1 into I of t. Okay, so the second variable is, state variable is I of t. So minus b by j omega of t plus k1 by j I of t plus 0 into u of t. Okay. U of t is the applied in voltage. Then x2 dot of t is di by dt. So what is the expression for di by dt? It is minus k2 by L omega of t minus r by L I of t plus 1 over L u of t minus k2 by L omega of t minus r by L I of t plus 1 over L u of t, and y of t is 1 0 x1 x2. So if you apply again, see, we have the ABCD matrix, D is 0. If you apply again C Si minus A inverse into B, you will get the transfer function. Any question?
Sir, that equation number 15, can you tell how we got that equation 15?
That is by law of motor that we discussed. We have discussed in the earlier, when we discussed the transfer function. The torque induced is proportional to the armature current. That is the law of motor. If it is a linear structure, then we have force. Force induced is proportional to the armature current. But since here we have a rotor, we call it a torque. Torque equal to K1 into I of t. K1, K2 are the proportionality constants. One is because of law of motor, other is because of law of generator. This we have discussed before when we were discussing transfer function. Any other question? Any other question? So somebody asked to give an example of 3 state variables. Okay, so here in this motor example, so if you consider angular velocity, then you have first order differential equation here, one for the torque, another for the voltage. So two first order differential equations, therefore 2 state variables. But if you consider position as the output, okay, if your application requires you to control the position of DC motor, then you need to use equation 13. When you use equation 13, you have one second order differential equation and another first order differential equation for the voltage. Second order differential equation for torque, first order differential equation for voltage. So you have totally third order system. Therefore, you need to use three state variables. So define x1 of t as theta of t, x2 of t as d theta by dt, and x3 of t as armature current. And you rewrite the state space model. You get a third order state space model. So that is there in the Franklin book also. You can verify that. For theta of t as the output, we have the third order state space model. Any other question? Okay, if there are no more questions, thank you.